Welcome to the 40th OpenValue meetup. We're still going strong even in these times of pandemic. My name is Roy Braam, I'm founder of OpenValue Amsterdam, and I will be your host of this meetup. This evening or this afternoon, we have two talks. One about remote debugging of Java applications by Wolfgang, which is also very interesting if you never write bugs like me. And the second talk is adversarial machine learning attacks and defenses by Alwin. So as a host, I will pass on the questions you place in the YouTube chat to the speaker. So let's start with introducing the first talk. It's an honor to introduce the first speaker, Wolfgang, with his introduction to remote debugging of Java applications. Wolfgang Liegel works as a full-stack software developer and DevOps guy at OpenValue Munich. Besides software development, he loves Linux and open source software and has been a Linux user for almost 20 years, which is quite awesome. He will give us an introduction to remote debugging, and he will demonstrate what you can do with a debugger connected to a remote Java application. Thanks for joining us, Wolfgang. And give him applause in the chat. The stream is all yours, Wolfgang.
Thanks, Roy. Thank you for having me. Hi. This is my first online live talk on OpenValue meetup, so I'm pretty excited to be here. And I'm happy to get the chance to talk about some stuff which also interests me as well. And it was quite fun preparing it. But let me first introduce myself. As already Roy said, I'm a full-stack Java developer at OpenValue. I have over 14 years of work experience. I'm doing development and operations. I really love Linux and open source software. And I can remember that I installed my first Linux almost 20 years ago. So it's quite some time. So I'm talk a little bit about remote debugging, give you an overview of the infrastructure, give some protocol details, and at the end, I will do some live demonstration. Okay, so what is remote debugging? Basically, this is nothing new. Remote debugging has been around for years. And yeah, while I'm talking about old technology, it's because I'm someone who wants to get to the bottom of things. I want to know how things work in the background. And the IDE does a lot of things for you and hides a lot of things from you. So you don't necessarily need to understand how things work in order to use them. And this is why I want to give some explanation and demonstration about how things are working, that you can get a better view of how the things are working in the background. So what are we doing? We are actually debugging an application like you would do in your local project in your local IDE. But the thing is, I'm gonna connect to a Java process on a remote host. During the debugging session, we can pause the application using breakpoints. We can step through instructions inside the code and look into variables and everything or almost everything which you could do in the debugging session on your local machine. Why do I remote debugging? Probably a lot of you have already heard the words, it works on my computer. Yeah, but sometimes it fails on production. Maybe it's some special constellation of how things are working together, and probably this fails and you don't know why it's failing. So you can keep on debugging on your local code, but you can also connect to some production-like environment and test the code in a production-like environment on your local machine. So this is something I would say it's a production-like environment. You have a web browser. You connect through a firewall to some server cluster with a database or database cluster in the back. So what I want to do is I need to pass the firewall. We are here in a production-like environment, so I need to pass somehow the firewall. And usually this is done by using some SSH jump server or something like this, which is a introduction, a single point where you can connect passing the firewall. And this is hardened, secured, that no external user who is not allowed on the machine or the production cluster can get access to it. Okay, so let's talk about a little bit about the protocol details. For debugging, I'm using the Java Platform Debugger Architecture, JPDA. This is an architecture for debugging Java applications. It provides standard interfaces for debugging, and this has been around for years. Yeah. And part of the JPDA is the Java Debugger Wire Protocol, which allows you to do remote debugging, which is a protocol for remote debugging of the JPDA. And it allows remote connections over network sockets. The instruction how I call it is Java with some arguments, and at the end I'm calling just a jar. I'm running a jar. And yeah, the other side is how do I connect to the remote application server? I use an SSH, which can use multiple jump servers transparently, and I can forward remote sockets to my local computer. So the debugging port, which I open in the Java application, I can forward through the SSH connection to my local machine. So basically, afterwards, I need to connect to localhost on the port, and this gets transported over the SSH connection. Okay, so let's start with the demonstration. I have created a server where we have a Java application. I'm gonna start this one now, and you can see it's listening for debugging connections on port 8000. And yeah, to use this one, I'm gonna do an SSH connection to the remote server, and I'm gonna forward my local port 8000 TCP on my local machine to the remote server. I'm directly connecting to the remote server, so it's from the point of view of the remote server, also localhost and port 8000. Okay, so I have a connection open now. Now let's check if things are working. I created some web page in here where you can refresh and you get a list with some data. The content is not important, but I want to just show you that this is a web page. And if I hit refresh, then you can see activity in here where the application is actually running. All right. Now I'm gonna open up my IDE. In this case, it's IntelliJ, but I think almost every IDE allows connection to some remote port. At least I know from Eclipse and IntelliJ. Maybe you ask your documentation, or maybe you can also ask me if you have any questions. Then I would look it up for you. Okay, so I set up some remote debugging configuration which connects, I'm sorry, it's quite tiny, but it connects here to localhost and port 8000, which is actually the port of my SSH connection, which I just opened up. So, and then I hit debug, and yeah, it's green. I'm connected to the target VM. And yeah, now I can start debugging. I'm gonna do some breakpoint and check if it stops. And yeah, it is stopping. I can step through the instructions. I can take a look at the variables. I have a local variable and a global variable. And yeah, not much special about it. So, and while I'm in the debugger, you can see that there is activity on the application side. So now you see open, then I step through, and you see the lines are appearing. Okay. So nothing special yet, if you're used to using a debugger. Let's make it more interesting and bring in a second client. So I'm at the first client. I'm restarting. I'm at the breakpoint, and then now I'm in a debugging session, and I want to say, okay, I don't want to disturb the other developers, so I'm removing or deactivating my breakpoint and let the others do. So this was quite yeah. When I was preparing the talk, then I stumbled upon this because now I have no breakpoint, and I'm reloading my page, and it doesn't go. And I thought, hey, what's going on here? Why is my application not working? I removed the breakpoint. What's going on here? And then I said, okay, I don't know, maybe there's a failure or so. And then I stepped through the code and went on. And then, okay, my page refreshed. So what's the missing point here? And then I realized that I'm just doing a regular breakpoint, which is by default stopping the whole JVM or the whole process. If you want to stop only for your own process or for your own thread, then you need to select here thread. And then let's try it again. So I'm stuck in the breakpoint. I will remove it. And then I hit refresh in here. And as you can see, this is working. And while I'm here in the debugging session. Yeah, which brings me to the next point. I'm currently in the debugging session, and I want to look at variables, and I want to try a little bit with the variables. And then I step over it, and okay, global is currently 0, so let's change this one. So I'm just setting it to 1, 2, 3, whatever. So now it's 1, 2, 3. And if I step over it, then you can see here global is 1, 2, 3. Now I hit refresh on my second client. And you can see the global variable is also 1, 2, 3. So this is something that you need to consider, that if this is running within a singleton, then your debugging session might affect other clients, even if they are not stopped by the breakpoint. So,
Wolfgang, yeah. I have a question already here in the chat. So I assume that the code in your local EDA needs to be in sync with the deployed code running on the server. But what happens actually if that's not the case?
That's a pretty good question. If it doesn't fit to the remote code, I can show you just right away. Then my IDE is smart enough to notice it. Yeah, you can still debug it, but you get funny effects, I would say. So I set a breakpoint. I added an additional line here, and then I will restart. And yeah, now it looks like I'm at this line, but actually, if I continue, then I don't see the line being printed because I'm one line above, actually. And then, sorry, no, actually, I'm one line below. Sorry. You see, if I step to the next point, I would expect to print out the local line, but the local line is already printed.
So can you say that the matching is done on the class name and line number?
Yes, you actually step through the binary code which is deployed on the remote machine. If it doesn't fit to your local code, then you get funny effects. Like, for example, if I place another few lines. Okay, this doesn't work while I'm in the debugging session, but now you can see. Sorry. Or if I remove some of the lines, then you can see also here this breakpoint, which formerly was here, is not active anymore. So I need to select a valid line, which is also valid on the binary code, which is deployed on the remote server. So now I start again here. Okay, so I think this was too much. Let's start it again. Okay, so now I'm here in my code, and as you can see, I would say that I already would have printed all the hashes, but if I step over it, then the hashes get printed now. And then I step, and then I am in a line which doesn't exist, or doesn't seem to exist. And then I step over the return, and I have to execute the curly braces. So yeah, funny effects, but it still works. You can still do it. All right. Yeah, as you already noticed, I can modify the global value, and I was able to affect other clients by modifying this global value. But what if I want to execute code which isn't already present? If you have done some debugging on your local machine, maybe you already have done something similar, but I think doing this on a remote machine makes it even more interesting to me, because what I am evaluating here is some code on the remote machine. So I need to step in the debugging mode. Okay, now I can start evaluate expression. This can be setting some variable, but I can also do some complex code in here. So Let's make it a little bit bigger. I'm doing some runtime execution in here, which is basically some shell commands. Yeah, I'm on a Linux machine, so I'm gonna call who am I. I'm gonna evaluate it. Sorry. Let's evaluate it. Okay, so who am I? It states Ubuntu. View text. Yeah, I'm Ubuntu. Okay. This is the user where the code is running. This is the user that I connected to, and I started the process. So nothing very spectacular or so. But since I'm on a remote machine, maybe I can take a look at some files. So let's evaluate this one. Okay, view that as text. Oh, okay. So now I'm able to see which users and therefore which services are installed on the remote machine. This is not so cool anymore if I expect that to be a hacker. And now what's really uncool is if the user which starts the Java process has sudo rights, which is pretty common if you are connecting with a normal user and start the process as a normal user, then you can see I'm root. So basically I can now evaluate any instruction over the remote debugging session with root rights. So since I'm expecting that debugging sessions is temporarily and the users are allowed to connect to the remote server, please be aware that if you leave some debugging session open, that this might imply some security risks. Okay. So I wanted to show you some little other thing. I think we still have a little bit of time. And what I wanted to show you is that I can not only do remote debugging, I can also do remote profiling. For this case, I installed JProfiler on my local machine and also on the remote machine. There's a third-party plugin required, which needs to be started with the process. And this opens another port. And therefore, I also need another port forwarding to that port. And yeah, then I can start some profiling application and say attach to the local port, which forwards to the remote machine. And then, as you can see, I'm able to look into the memory consumption, how many classes are loaded, how many threads are currently running, CPO load, and also you can take a look at the heap, the loaded classes, the loaded objects in your application, and yeah, you can see there are some objects in here. let's take a look for our forwarding controller, which we are debugging all the time. And yeah, let's analyze some references and also show in graph, which I always think this is quite handsome to get a graphical overview how things are connected to each other. And you can also open up and get some references. And then you can profile the application from a very different point of view. Okay, so that's basically it, what I wanted to show you. Are you having any questions or comments?
So are there any questions or comments? Please fill them into the chat. I have at least one. So normally when I have trouble with this kind of things when I have to go through a couple of stepstones. So how are you handling, for example, debugging remotely if you need to go through multiple machines?
Okay, that's a good question. You can use parameters to the SSH server, to the SSH command, which allows you to jump over servers. But my favorite is using SSH configuration, which is in here. And right now, you can see that I'm directly connecting to the meetup host. But if I want to connect over some proxy host, then I can use, for example, like this. I can maybe say host jump. Host name is jump. And yeah, maybe you have to use a different user to connect to the jump server. Maybe you also need some different port. I don't know, whatever. And then you can say to connect to the meetup host, I want to use the jump server in between. This is by using the proxy jump. And then you refer to the name of the jump server, which is here. So, and using this, you can also concatenate multiple host configurations. And yeah, in this way, you can jump through over multiple jump hosts to your final destination.
Okay, cool. Thank you. There's another question. You show us a profiling tool rather quickly about when you profile. So what do you need for this profiling tool, and what's the name of this profiling tool?
The profiling tool is JProfiler, which has also been around for plenty of years. This is a evaluation version, but this is a commercial tool. But there are also a lot of other profiling, Java profiling tools around. I would say I can't recommend one special profiling tool. You need to select the one which fits best for your problem.
Great, thanks. There's another question. So you told us that it's kind of dangerous for having debugging ports open and showing us what you can do. So how can you identify these ports, like for example in a port scan?
How can you identify? This is a really interesting question. I would say unless this is a well-known port, right now I have no idea how to identify it only by connecting to it. Maybe if you suspect this to be a debugging port, then you can try to connect a debugger to that port, or maybe provide some commands on this. But yeah, right now I'm don't know exactly if you can really identify it.
Okay, thank you. Another question. Most of the time, so when I want to debug a remote application, I'm too late with debugging and it already started. So especially when I want to debug something in the beginning. So is there a way that I can actually start a debugger on the right time when it starts the application, or the other way around? Because then I'm not too late for the startup debugging.
Yeah, actually, this is pretty easy, which I can show you here. So if I wait a second, I'll make it a little bit bigger. So this is my my prompt here, and these are the arguments that I am passing. And here is a little suspend no. I just need to set it to yes, and afterwards the application waits until some debugger is connected. So let me show. I will connect my debug. Now I'm connected, and then the application starts up.
Cool. Thank you.
Thank you. Thank you for
Are there any more questions? You can. If there are no other questions anymore, then I want to thank you, Wolfgang. I really enjoyed your talk. Hope to see you soon in real life, maybe somewhere on a different conference. Let's see. But thanks.
Yeah. Maybe there's an appointment in September in Munich for you.
Cool. Thank you. Awesome. Okay, thank you, Wolfgang. I really enjoyed it. For those who want to still ask questions, you can put them in the chat. I think Wolfgang is there to answer them still. For the next talk, let's have a break till 1940 Central European time, so 7 minutes from now. And then we will start with a second talk from Alwin. Okay, see you soon.
Thank you.
Hi, welcome again and thanks for tuning in. Let's get started with Alwin Peppels talking about the talk Fooling Robots and Building Better Ones for Serial Machine Learning Attacks and Defenses. Alwin is a security specialist at CyberSeals. He's a security researcher working mainly as a consultant for financial and governmental organizations. He did some of the responsible disclosures in his free time, which even gave him a spot on the Microsoft, Philips, and Google Hall of Fame for it. Thanks for joining us, Alwin. It's a pleasure. Give him applause in the chat, and the stream is all yours.
Thanks, Roy. Thanks for the great introduction, and welcome everyone to my talk. Indeed, fooling robots and building better ones, about attacking machine learning models and possible defenses. So, who am I? Yeah, as I was introduced, Alwin Peppels, I'm a security enthusiast. I like to build stuff, tinker with stuff. And I like most things with technology, digital technology, information technology, and logs. Especially the combination of those is something I enjoy working on. And in my day job, I'm a penetration tester and a consultant. At the moment, I'm second at ING, and yeah, I really like it there. So I enjoy breaking stuff and then helping the people fix it. So what we'll talk about is some ways in which we can break machine learning, because that can often happen in novel ways. And then we'll go over some of the things we can undertake to maybe mitigate that risk and make sure that someone who has bad intentions is not able to influence our models and architecture. And if you have any questions, just feel free to ask them in the chat, and we'll definitely get to them by the end. So the reason for giving this talk is that machine learning can go wrong in a lot of ways. In a lot of new ways, also depending on the architecture that you're using for the purpose that you're using it for. There are a lot of security issues which have sort of been present since the 90s and which have given people in IT a headache and which we've been forced to deal with. Machine learning has introduced some ways in which that can go wrong, which we're not familiar with. It's something from the recent years. Also the boom in machine learning and deep learning has only really taken off in the last 10 or 5 years. And the security guidance on this is somewhat lacking. The attacks which I'll discuss in this talk have also been discovered only a few years ago. And the mitigations for it, the architectures which might resist them, are just being invented, and it's still somewhat of an open problem. We'll talk about a few ways in which it can go wrong, which are not really unique to machine learning itself, not really inherent to it, but are more a property of how it's used. And then we'll go into some attacks which are specific to machine learning and linear models, which are called adversarial examples. And we'll also go over why they work better than most people think. Now, if it's vulnerable to adversarial examples and you want to fix that, it's usually a very expensive fix. So in the best case, you need to spin up your GPUs again and train the model, which is a huge computational effort. And in the worst case, you might need to throw out your architecture entirely and start from something which is more robust as a design goal. So a lot of these things will not be fixable with a small pull request. And for defending against the adversarial examples, you also need to generate them yourself so that the model can incorporate them in the training process. So it's very important to know how to make them. You don't really need to understand how the insides work. You do need to understand how to make them if you work with these models and try to defend against it. And of course, if you're building something, it's very important to know how to break what you're building, how other people are going to try to break what you're building, or at least have someone near you which knows how to break those things. And also for making sure that time is spent fixing these things, it's often important to have a working proof of concept. So there are 3 general classifications basically of what can go wrong. There's evasion or confusion, which deals with having inputs misclassified. There's poisoning, which has to do with putting a backdoor in the model or disrupting a model which is doing online learning. And there's also multiple ways information can leak. So people might try to steal the model, the parameters of the model to be exact, or they might try to leak training data or information about the training data, which is called inference. And there's a nice diagram which shows the different ways in which that can go wrong, which I've shamelessly stolen from the adversarial robustness toolbox, which is a tool we'll get into later in the talk. So leaking information, we can ask certain questions, like is a record a part of the training data? There might be some autocomplete, which is trained on internal emails by employees. And then we can simply try to have it autocomplete a sentence like the social security number of this and this person is, and the model might actually try to fill in the social security number if it's seen that in the text, because the transition probabilities of those characters will line up, and it might actually spit it out. And if we know that a person has been part of the training data, can we ask if it's been part of a specific class? So if we have a medical training model, a model which has been trained on medical data, can we find out whether a record was part of a certain class? So if someone has a specific diagnosis. And trying to infer parameters of a model might also be useful if we say want to attack a trading bot. If we know why a trading bot is acting in a certain way and when it acts, we might be able to predict its movement and make money off of it. Poisoning a model is something that might happen if people want to have a lasting impact. If you manipulate the parameters, the model will continue to behave in a defective way. So it's very important that the training data is vetted and that it's from a trusted source. It must be clean, basically. There's already a problem with models taking over the bias which is present in the data. And trying to avoid that is actually a tricky thing. So if people try to bias the data on purpose, that might be even harder to detect and prevent. And for things doing online learning, it's very important that people don't poison the data, usually because it's very accessible. And if you want to have a look at how that can go wrong, just look at the T-bot by Microsoft on Twitter, which people quickly found out that it was learning from the tweets, and they tried to make it say obscene things, which they succeeded in within 24 hours, basically. Now, the broadest category is evasion and confusion. This can happen in a lot of ways. So malware or spam might try to evade detection. Someone might try to craft a piece of audio, which can be played over speakers, or put in an ad, which people don't recognize as a voice command, but which might tell your Alexa or Google Assistant to do something weird, like open the garage. People have poured sand on roads to disrupt self-driving cars, which is a very low-tech analog attack, but it was nonetheless very effective. People have been pumping the prices of certain cryptocurrencies by spamming Twitter with positive words related to those cryptocurrencies. And then there were trading bots which were acting based on sentiment, which then started buying those prices, pumping them up. And the bottom one is quite a funny one. Someone took a trolley full of smartphones and started driving them very slowly across a bridge, which made it show up as a traffic jam on Google Maps, and basically cleared out the bridge because Google Maps was telling everyone to take a different route. But it's also a bit of a low-tech attack, which is very hard to defend against. And then we'll get to a specific case of evasion, which are adversarial examples. You might try to take an input, which is classified correctly, and then modify it in a very slight way to see if we can have it misclassified. And usually for linear models, which neural networks in essence also are, this is very doable, and often we don't have to change the input that much for it to be misclassified. And also shout out to Ian Goodfellow for pioneering most of this work and some excellent talks and lectures which he's given on the topic, and the work that he continues to do. He's a very interesting guy, you should check him out. So the classical adversarial example uses a panda. So we take the input image, a panda, which is classified with around 60% confidence. And then we're able to find some data. It's not noise as stated here, it's very specific data, which if we add it to it just a little bit, we can have the input misclassified in a horrible way. So here we add less than 1% of that noise to the image, and the image basically looks the same. I think if this is an 8-bit monitor, it might even be the images might literally be the same. But we're able to find a bit of data that if we add it to the Panda, we can have it horribly misclassified. And that's called the adversarial perturbation. And we can see this working very well for deep neural networks, but this works for basically any linear model, support vector machines, logistic regression, you name it. And there's a nice little demo online because this technique can be done without very much computation power. We basically have a closed form for it. So we can upload our own image in the AdVis online tool. I've used the seal as an example. We can crop that and we see that it's classified with 90% confidence as a sea lion. And then we can tell the web app to find the adversarial perturbation for us and add it with a very small epsilon. So let me see if I can move that over to like 1%. It probably needs to think for a bit. There we are. And we can see that the image classification model has is no longer classifying it as a sea lion, no longer correctly, and it's now classifying it as an otter with 92% confidence, which is a bit more than it thought the sea lion was. And we still can see that the image hasn't changed by that much. If we crank the epsilon up, we'll see the adversarial perturbation shining through, basically, because then it's no longer properly hidden, and it'll have to think for a bit, calculate it, and it should be showing up around now. Well, apparently it can't handle me streaming it and demoing it at the same time. There we are. But we can see the adversarial perturbation shining through, and the sea lion has started to look a bit creepy, and now it's classifying it as a shower curtain. But we can see that with a very small epsilon, the image stays almost unchanged, and we can have the model misbehave in a quite serious way. And also interesting to play with, for example, we have the activation map, and we can see what part of the image the model is basing its decisions upon. It's a very interesting web app to play with, and at the bottom there's a lot of explanation on what's going on. So if you want to do this yourself, I can really recommend the Adversarial Robustness Toolbox, ART. It provides a lot of very convenient tools which work out of the box. So you can just import the fast gradient sign method, give it the classifier and the epsilon, the amount you wanted to move the image, and you can quite quickly generate the adversarial example and have it classified wrongly. So this is sort of what you need to demonstrate it and also to fix it, as I'll demonstrate later on, as I'll go over later on. But I do want to dive a bit into the technicals of how this works. If you don't work with mathematics or the internals of machine learning a lot, you don't really, it's not essential, but I do want to dive into it so people might understand how it works. So if we think about how a machine learning model learns, in this case, a deep neural network, which does gradient descent to optimize its parameters, we might visualize the actions of learning as the model sort of walking over a landscape of the error. So we have two model parameters, theta 0 and 1, on the horizontal axis, and then in the vertical axis we have the loss of those two parameters at given points. And then for each training step, we calculate the slope of where we're standing, basically. We calculate the gradient to find out which direction is downhill. And then the training of the machine learning model is basically walking down to the lowest error. Using the false gradient sign method, we basically do the opposite of this. Now, if you're used to calculating the gradient, you usually do that over the parameters. So you're asking the question, which direction should I nudge the weights in order to increase the accuracy to make the model better. You usually find out the slope and then walk downhill by adding minus sign. But using backpropagation, we can just calculate, we can take it a step further, calculate it over the input itself. And then the model's already done training, the parameters stay the same, but we're asking the questions, which direction should we nudge the pixels in order to have it classified wrongly? So in the case of the panda, we calculate the loss J over the model parameters theta, given the input image X and the target label Y. And then we take the gradient against the input image and then take the sign of that. The sign operator here is a bit of a regularization. So we prevent the image from being modified by more than epsilon. So we just take the direction and make sure all the pixels are modified exactly by epsilon amount. In this case, 0.7%. And if we can only modify a small part of the input, we might still just take the argmax, so the most potent pixel, the one which has the highest direction, the highest slope associated with it. We might still have the image misclassified if we're only able to change a very small bit. So the intuition for these things when you first learn about them might be that they're very rare, that the deep neural network has some weird corners where these adversarial examples live, and that they are unique to the model. But as people looked at it a bit more, that turned out not to be true. It's more like underfitting, actually. The models are too linear, and they don't encompass the shape of the data well. So if you look at the adversarial examples, they actually live in a quite high dimensional space, making them more robust than most people think. And that's actually really bad news. Because, of course, the first step to preventing this is keeping the model a secret, just making sure that other people don't get an exact copy of your parameters. But seeing as these adversarial examples are not really unique to a single model, and they live in a somewhat high dimensional space which multiple models share, an attacker might just train their own surrogate model. They might just train something which looks like your model and find an adversarial example for that. And the adversarial example is actually likely to work on your model as well. And they might use that to mount physical attacks or generate adversarial examples which are robust. So here's some interesting research by Google. They tried to find something which is basically an adversarial object, just a sticker which you can place on stuff to have it misclassified. So the example here is a banana, which is misclassified as a toaster. And what they're basically doing is they're finding the image which is the most salient example of a toaster to a whole bunch of neural networks. So they make a surrogate model. They actually make a few of them. They make an ensemble. And then they do a lot of optimization steps, a lot of effort to find the adversarial input image, which fools most of the models most of the time. So they try to pick something which is universal and shared across multiple architectures. And by doing that, and also making it robust to scale and rotation, you can have something which is actually very useful in the real world. The fast gradient sign method, which I showed, the very subtle noise is not very robust to rotation, and it's very specific to that model. So you'll have to do a lot more effort to make sure that it generalizes, but it can be done. Good news for the attackers is, for the defenders, sorry, is that this is more detectable. In other words, the sticker just looks weird, and if you see it on an image, if a person sees this on an image, they might very well be alerted to the fact that someone is trying to manipulate the input. So what can be done? It's actually surprisingly hard to defend against this, the adversarial examples. A lot of research comes out and claims that they found something which helps against this, but then they've only beaten the fast gradient sign method. A lot of the mitigations are actually not robust to multiple optimization steps, or an attacker which expends more computational resources to find something. They, from the looks of it, the adversarial examples are a bit universal and are quite hard to prevent. But one of the things which works best is adversarial training. So that's basically training it for an epoch, then trying to create adversarial examples which fool the model, and then adding that to the training data. Then you can train the model on the adversarial examples, and it will become more robust to them. Then you can generate a new adversarial example which is better and stronger, and you can do that iteratively until it balances out. And that turns out to be one of the best ways to make it more robust. And it's one of the tactics which is universal to how the tech giants are trying to prevent this. Some people have also had some success using things like denoising autoencoders or ensembles, which are of course harder to fool because they you have to fool multiple models and get a consensus. And for decision trees, there are special versions. Oh, my bad. There are special versions which are available, which are actually more robust to this. A normal decision tree will just try to find a boundary which separates the data as best as possible. But the special robust decision trees, they try to look at the distance from the decision boundary. So they try to optimize sort of the, they try to put an upper bound on the impact that adversarial examples can have. There's also a lot of operational defenses. Not disclosing the model is probably one of the best ones. Use, if it's security sensitive, use something which has been made in-house and don't disclose it. But as we saw, that's not always enough. Giving out hard labels instead of probabilities is also a very important one. If you give people very nuanced feedback on how the model classifies modifications in the input and how that changes, one might just do a very, quite efficient random search by just permutating the input, seeing if it increases or decreases one of the classes it's recognized as, and only keep the changes which increase the probability. This was actually the case for a proof point spam filter. The spam filter gave back a header stating its confidence that the input was spam, and people were able to construct basically an example which was never recognized as spam just by adding some random data to the end. If you do have to give out some nuance, try to see if you can round them to a near number, quantize them, make sure you don't give people something which is differentiable. Don't give them a smooth slope to walk up or down on, basically. Using explainable machine learning models where possible is always great. If something goes wrong, you can at least look in the brains of why it went wrong and maybe even manually fix it, which is not possible for a lot of deep neural networks. Training data should be completely trusted, basically. Everything that goes into the training data will end up in the model. So that's very, that's basically what you're getting your performance from. Also in the case of, for example, the Twitter bots, which are pumping the price of some crypto, you could just blocklist those or create an allow list of accounts the trading bot is allowed to look at. You could verify data using multiple sources. For adversarial examples, for facial recognition, it turned out that using multiple cameras was a great way to prevent that. But also look at other operational defenses, like implementing rate limiting. If you do disclose one of those headers, like the spam filter did, make sure that people can't repeatedly probe the model. And also keep humans in the loop. If there's anything going wrong, make sure that people are alerted. Set up something which does proper monitoring and yeah, it's better even to do proactive alerts. So if anything weird happens, if you get a sample which is far outside of your statistical distribution, maybe bump it up for manual review, or have a human look at the performance of the model from time to time to make sure nothing weird's happening. And how to play with this, I can really recommend the Adversarial Robustness Toolkit, which will support most libraries, whether you work with TensorFlow or Keras or sklearn or one of the gradient boosting libraries. It will have something for you. And you can use this to attack your own model and create adversarial examples which are used during training, but it also offers a lot of great models which are actually robust to these adversarial examples. And besides that, it also has tools for extraction of model parameters from other models, inferring the data. And it just has a lot of great documentation and code examples to start playing with it. SecML and CleverHand also deserve a mention here. SecML has a great read the docs page, which you can use to walk through some of the tutorials on machine learning attacks, and they have some great guidance on getting started and on the math behind it. And yeah, being able to generate them is the most powerful way to recognize the danger for this, to crystallize it for your colleagues and perhaps management. And it's also powerful to play with and actually necessary to the adversarial training, which might be the way we can use to prevent this. And that was it. Here are some of the resources which I've mentioned, and some other guides which you might use to get yourself more familiar with this. And I think I'll give it over to Roy for questions.
Yeah, thanks, Alwin. Yeah, there are some questions. There's still time left to ask questions in the chat, so please feel free. So Bert-Jan's asking for a friend. So how doable will it be to stick a sticker to the back of your car to confuse the camera-based lane systems of cars behind you, for example? Like the example with the banana and the sticker, like is there something, how doable would it be to do this with a car system?
That's actually a really good question. For a lot of the more complex image recognition tasks, which it does, it could be very doable. For the specific case of the lane keeping system, which is used in some self-driving cars, that probably won't work because they do a lot of filtering on the image. I happen to know that they do a lot of sort of quantization and line detection. It's actually very simple what they do for the lane keeping. So you need to go more low tech. It just responds to white lines. So if you would be able to place a long white sticker on the road or place some salt on the road and create a long enough white line, you will definitely confuse it. Using a sticker, you'd probably be able to have it recognize someone as, recognize your car as a person on the highway, or recognize your car as a motorcycle, because that uses a more complex image detection network.
Good, thanks. So another question was, but I think you already answered the question later on in your presentation. One of the questions was from Roy Wassa. The attack you showed with the images, would it require multiple images of the same object? Would it help you actually to prevent these kind of attacks?
Yeah, that's actually a good one. If you're talking about adversarial examples in the real world, like those stickers or 3D objects, which might fool image classifiers, then it's always great to have multiple perspectives. There's also a great Black Hat talk, which discusses this defense. And what's mentioned there, for example, is that if the angle of the cameras is made wider, that's actually more effective. So the more images you have from and the more different the perspectives are, the more effective the mitigation.
Okay, cool, thanks. Another question. So you showed us a couple of different attacks. So do you know any of these misuses of any of these attacks? Are there any known misuses?
Yeah. The case where crypto prices were pumped up using Twitter bots, that's a real example. There are quite a few others. The spam detection invasion, that's also a real example, where a proof point firewall, a proof point spam detection system was circumvented that way. That has a CVE associated with it, and before that time, you could create spam which was not picked up by the network. There's a lot of things which can also be used in the real world. The guy with the shopping cart, the trolley full of mobile phones, actually caused quite a stir because he disrupted traffic so heavily.
Cool, thanks. So another question. So what are your thoughts, your personal thoughts about using AI everywhere in the world in general, given the fact that it can be attacked like this in a new way?
I think we'll have to be very mindful. I think how enthusiastically, how zealously it's being used might not take into account how effective these attacks are and how well they transfer between models. I think that's a very overlooked characteristic. I think adversarial examples are a bit misunderstood maybe, or underestimated. And I think a lot of people train a machine learning model sort of with the assumption that everything that the model will see after that is from the same statistical distribution. That's an assumption that a lot of people forget when they're training a model, and that sets it up for terrible failure depending on what the model is used for. I do think, for example, with people having stop signs misclassified and impacting self-driving cars, you can already sabotage cars, just not in such a fancy way, but it's already very doable, and people don't tend to do it because people don't generally want to inflict harm upon others. So I do think we'll be able to survive with self-driving cars and these attacks. But it's definitely something to watch out for, especially if you're using machine learning to make financial decisions or steer other important things in the world.
Okay, cool. Thanks.
Anytime.
So there are no further questions anymore.
All right.
Popping up. So thanks, Alwin. A really awesome talk. I really enjoyed. I learned something. So tomorrow I will buy a couple of phones and connect them to Google and drive them very slowly to our street, so it will reduce traffic.
Make sure you don't mention
Sorry?
Make sure you don't mention my name.
Sure. Yeah, thanks.
Hey, thanks for having me, and have a good evening.
Same to you. So with this, we are at the end of our 14th meetup. Thanks for joining, and I hope to see you next time. Thanks.